Hi, welcome to the fourth video on module 2 of radar cross-section of targets, which is the part 2 of module 2 in our radar engineering subject. So in the last video, we had discussed about probability of false alarm and probability of detection. I also showed you the notes and the video question paper, which had the question related to it. The envelope detector and the probabilities, that is PFA and PT. Now today we'll discuss the next topic. So this is the part 2 of module 2. I'll just show you the syllabus again. So radar cross-section of targets. Okay. Now today in this video we'll be dealing with simple targets, sphere and cone sphere. Okay. So let us start. Yeah. So radar cross-section of targets. So here we are talking about sigma. So in the first top module, where we were talking about radar range equation, we have a term called sigma, which has the units of area, right? So this is radar cross-section, that is target cross-section. Okay. So this sigma is the property of a scattering object or the target, which is included in this radar range equation, and it represents the magnitude of echo signal which is returned to the radar by the target, right? So it was, what was the equation till the re-radiated power density back at the radar? It was this, right? It was this. So this is the power density of the echo signal, which is re-radiated back at the radar. So PT was the power transmitting peak power. PT by 4 pi r square was the power density. G is the gain when we consider a directive antenna. So this is the power density for directive antenna. And then when it hits the target, we have something called as sigma, right? So sigma by 4 pi r square again, so that we have the power density, not the power, right? Power density, which is re-radiated back at the radar. So this is one definition, but there is still another definition of sigma. So it is given as power. The meaning is the same, but the expression is the power reflected towards the source. Source means the radar, right? The transmitting antenna. So power reflected towards the source per unit solid angle. I hope you remember what is solid angle. So power reflected towards source per unit solid angle divided by the incident power density. This incident power density by again 4 pi. 4 pi is the solid angle of the entire sphere, right? Right. So this is the expression. So ER is the R is the range to the target, which we know, and ER, and we don't know the limits, right? So R tends to infinity. So ER is the electric field strength of the echo signal, which is radiating back to the radar, and EI is the electric field strength incident on the target, right? So this is the same. Okay, so I hope you have understood this. Now, sometimes this radar cross section is said to be a fictional area, which intercepts a part of the power incident at the target. Okay, so if this power is scattered uniformly in all the directions, it produces the echo power at the radar, which is equal to that which is produced at the radar by a real target. Okay, so I'll just say that again. So sometimes this radar cross section is assumed to be a fictional area. It intercepts a part of the power incident at the target, correct? Right? So it doesn't. So the entire power which is coming from the radar doesn't hit the entire target. So the target intercepts only a part of the power incident at the target. Now, if this is scattered uniformly in all the directions, this radiated power, if it is scattered uniformly in all the directions, it produces the echo at the radar, that is the power density at the radar, which is equal to that produced at the radar by a real target. Okay, so that's why we are considering the sigma, that is radar cross section. But real targets actually do not scatter the incident energy uniformly in all the directions. Okay, and larger the target size, larger cross section is likely to be correct, right? I mean the intercepting area would be more, right? Now, so this is the problem. The real targets do not scatter uniformly in all the directions. So this power scattered by a target in the direction of radar receiver, and hence the radar cross section can be calculated by solving. Usually it is calculated by solving Maxwell's equation with proper boundary conditions, or also computer modeling could be used. Okay, so this is how we usually calculate it now. So this is a figure which shows the radar cross section. So it could be like a target could be like this. It could be like this, right? So we don't know. So this is a complex target. So just now we saw the expression, another definition of sigma. So it's the same thing, projected cross section to reflectivity into directivity. So we saw 4 pi r square into ER by EI the whole square. So why do we have ER by EI the whole square? Because it is power, right? So ER and EI are equivalent to voltages, right? So we have square. So ER by, since we need power, power reflected towards source per unit solid angle by power incident, power density incident per 4 pi. So that's why we have ER by EI the whole square into 4 pi r square. So usually we have complex targets like this. And this is some simple target, and it's a shape of a sphere. So if you see here, this is the radar side. So the incident power will hit only this much part of the radar cross section, not the entire thing, but still, if this incident power is scattered uniformly in all the directions, the effect would be same as that of a real target. Okay? So sometimes the sigma of complex targets can be calculated by describing the target as a collection of simple shapes, okay, whose cross sections are known. Like for example, this cross section is known. We know that it's a sphere. So, but then here we will not know. So that's why for complex targets, it is calculated, the sigma of a complex target is calculated by describing the target as a collection of simple shapes, and then the total cross section is obtained by summing vectorically the contributions from the individual simple shapes. Okay, so that's how it is usually done. Now, yeah, so this is what I just said. So usually we calculate the sigma using Maxwell's equation with proper boundary conditions or by computer modeling. And then I just said, usually we cut them into simple shapes, and then we summing vectorically the contributions from individual simple shapes, we get the complex target. Okay. Now, so the first simple shape which we are talking about is going to be a sphere. Okay, so this is the simplest object for illustrating a radar scattering, since it has the same shape no matter from which aspect it is viewed, right? So from whichever side you see, it will have a shape of a sphere itself. So sphere is a sphere no matter what aspect it is viewed from. Its cross section will not be aspect sensitive, right? So no matter from which side you see, from which aspect you see, it is having the same shape. So the cross section of other objects, like not sphere, will depend on the direction it is viewed, correct? The sphere, from whichever direction you view, it will look like a sphere, but then other shapes will not look the same from different views, right? Now, so I'll directly go to one figure, this one. So this is a very important figure. So when a video question is asked on sphere, so you have to draw this graph. So this graph has sigma on the y-axis and circumference on the x-axis, but the normalized versions of both. So sigma is normalized using the projected area, that is pi a square, and circumference is normalized using, what is the unit of circumference? It is meter or centimeter. So it is normalized using lambda, which is also measured in meter or centimeter, right? Now, so in this figure, so we are going to see three different regions. That is, the first is Rayleigh region, second is me or resonance region, and the third is optical region. So yeah, so first let us see what are these regions. So here in Rayleigh region, this 2 pi a by lambda is the circumference by wavelength. This, what is a? A is the radius, okay? Yeah. And lambda is the wavelength. Now this 2 pi a by lambda in Rayleigh region is much lesser than 1, right? You can see that this is lesser than. And in optical region, 2 pi a by lambda is much greater than. Okay, so that's the main difference. Now, what does this mean? Radar cross section depends on the characteristics dimensions of the object compared to lambda. Okay, so when lambda is very large compared to the object's dimensions, right? You can see this. So this is the corresponding to object's dimensions, and this is the wavelength. So if lambda is very large, what will happen? This whole thing becomes small. That means this side. Right? So when lambda is very large compared to the object dimensions, scattering is said to be in the Rayleigh region. The radar cross section in Rayleigh region is proportional to 4th power of frequency, that is f power 4 or lambda to the power minus 4. Okay, so lambda to the power minus 4. So here the radar cross section is proportional to lambda to the power minus 4 or f power 4. And it is determined more by the volume of the scatterer, that is volume of the object, and but not by the shape. Okay, so we are talking about Rayleigh region here. Now what is the other extreme? Optical region. In this other extreme, lambda is much small, right? So lambda is small, that means this is going to be large, 2 pi by lambda. So here we are, the other extreme, 2 pi by lambda is much greater than 1. So that's optical region. And this sigma is affected more by the shape of the object than by its projected area. Okay, so that's the main difference between these two. Okay, so in Rayleigh region, it is affected more by the volume than the shape. Here it is affected more by the shape of the objects than the projected area. Okay, now the third one is me or resonance region in between Rayleigh and optical. So here, the radar wavelength is comparable to the object's dimensions. Okay, so that's one point. Now let us come in detail about all these three areas. So the first is Rayleigh. So Rayleigh here, 2 pi by lambda is much lesser than 1. So sigma is proportional to lambda to the power minus 4 or f to the power 4. And here the sigma depends on the volume of the object than the shape. Now, in optical region, we have 2 pi a by lambda much greater than 1. So here, so you can see here, so this part. So where is this part coinciding? It is exactly equal to 1. That means sigma, that is radar cross section, approaches the physical area of the sphere. So sigma by pi a square is equal to 1, right? So sigma by pi a square is equal to 1. That means sigma approaches is equal to pi a square. Approaches the physical area of the sphere as the frequency is increased. That is lambda is small, right? But this can mislead us into thinking that the geometrical area of the target is a measure of radar cross section, but it applies only to, what are we talking about? Only to sphere, right? Yeah, not for the other shapes. Now, so in optical region, scattering does not place over the entire hemisphere that faces the radar. Okay, but only see. So you can imagine a sphere getting hit by the incident power. So do you think the entire, one second. Yeah. So say this. So if it is hitting the sphere, it doesn't hit the entire sphere, correct? So it applies only to only a small bright spot here. Only a small bright spot at the tip of the smooth sphere is actually hit, correct? So the only illumination is at the tip rather than the entire hemispherical surface, right? So that is one point. Yeah. So so that was about optical region. Now next is me or resonance region. The radar cross section of the sphere in resonance region oscillates, correct? So this is sigma. So oscillates as a function of frequency, or 2 pi by lambda. The maximum of this occurs at what? So this whole figure, where is the maximum? Here. So this maximum occurs at 2 pi a by lambda is equal to 1, right? So this maximum occurs as 2 pi a by lambda is equal to 1. And this is how far from this line. So the optical region is at 1, right? So this is the, so if you see, this is the line of optical region. So this much is 5.6 dB greater than the value at optical region, right? And the first null, which is the first null, this one. So this is actually 5.5 dB below the optical region. The changes in cross section occur with changing frequency because there are two waves. So why are these fluctuations happening in me region? Because there are two waves that interfere constructively and destructively. Okay, so that is about me or resonance region, right? Me or resonance region. Now, so I'll just show you one more figure. I just said this changes in cross section. This changes in cross section with changing frequency, that is indirectly lambda, is because there are two waves that interfere constructively and destructively. One is the direct reflection. Okay. Yeah. One is the direct reflection from the front face. So this one. So this is the direct reflection. So this is called a specular return. Okay. The other one is, it is called a specular return. The other, this is direct reflection. The other one is creeping wave that travels around the back of the sphere and returns to the radar. So this is creeping wave. So these are the two waves which interfere constructively and destructively. So that's why we have fluctuations in me or resonance region. Okay, so the other figure is so electric field versus distance. So this is the specular return. Okay, the direct reflection. This is the creeping wave with lesser amplitude. Okay. Now, the longer the electrical path that is around the sphere, greater are the losses. Okay, so smaller will be the magnitude of the fluctuation with increasing frequency. Okay, yeah. So this is one point to be noted about me or resonance region. Okay, so I'll just go back to a few things more about these regions. So I'll just give you the gist of every region. So let us go back to whatever I've said in the slide. So Rayleigh scattering, as we said, it is 2 pi a by lambda much lesser than 1. And it is dependent on the size of the particles and wavelength. Okay. Now this intensity of Rayleigh scattered radiation increases rapidly as ratio of particle size to wavelength increases, right? 2 pi a by lambda increases. As 2 pi a by lambda increases, this intensity increases, right? Now, so as we said, sigma is proportional to fourth power of wavelength, right? Inversely proportional to fourth power of wavelength or directly proportional to f power 4. So usually echo from rain is described by this Rayleigh scattering. Other examples are this blues color of daytime sky and the red blues color of daytime sky and the reddening of sun at the sunset time. All these are because of Rayleigh scattering. These are some examples. Okay. Next was me scattering. So here, May scattering suggests situations where size of the particles, I just said that, where the size of the particles are comparable to the wavelength, right? So rather than much smaller or larger, it is almost comparable. So these are some examples. Dust, the scattering because of dust, pollen, smoke, and water, microscopic water droplets are because of May scattering. That is usually where the particles are at the lower portions of the atmosphere. There we have May scattering. Okay, and here we have oscillatory. Cross section is sigma is oscillatory with frequency. Correct. So that was because of the two waves I just showed you, the specular return and the creeping wave. The third one is optical region where 2 pi by lambda is much greater than 1. That is on the other side, this side of the graph, right? So here, since in optical region we have 2 pi by lambda is what is the value of sigma by pi a square? It is exactly equal to 1. That's why sigma approaches optical cross section, that is projected cross section pi a square. Okay. Now, I just said in this region, the incident power is exactly hitting only the tip of the sphere. But then it applies only to the sphere, not to other targets, right? Now, yeah, that's what I said. Yeah, and then I told you about this 5.6 dB in the figure, right? In the maximum value of the graph, and which is 5.6 dB above the optical region. Optical region is at 2 pi a by lambda is equal to 1. And then we spoke about the two waves which interfere constructively and destructively in the near region. One is the direct reflection, which is specular return, and one is the creeping wave, which is from the back of the sphere and returns to the radar. Okay. Yeah, we just saw this figure. Okay, so that was about sphere. All these three regions are applicable only to sphere. Okay, so that was one of the simple targets. The second simple target is cone sphere. Okay, so this cone sphere looks like this. So it has a base which is capped. So this is base which is capped with a sphere. So a sphere looks like a cap to this cone. Okay. So this is how a cone sphere looks like. So sphere is the simplest one because from whichever side you see it is the same. But then cone sphere, this side is different, this side is different, this side is different, right? Now when we take the first derivatives of a cone and sphere at this point, this joining point, the first derivatives of the cone and sphere contours are equal at the joint between them. Okay, fine. Yeah. Now this, so in sphere we didn't have a graph like this. We had three regions. So this is the same x-axis and y-axis, sigma by pi a square in y-axis and 2 pi by lambda in x-axis. But the graph is different for a cone sphere. Okay. Now, the cross section of the cone sphere can be very low on the nose on. So we have two things. One is nose on aspect. Nose on aspect is this side. So when you hit from this side, so this is facing the radar. So this is nose on nose, this part, nose on aspect. And the other one is from the rear. So this is the rear part. Okay. So from the nose on aspect, the radar cross section does not depend significantly on the cone angle. Okay, it does not depend on this cone angle or volume. From the rear, the cross section is that of a sphere, correct, right? This cross section is like a sphere. Hence, it is much larger than the cross section viewed from this part, correct? Now, larger value. Above this, the larger value of cross section also occurs when the radar is viewed when cone is perpendicular to the surface. So from this part. So if this is the front, if the incident power is hitting this way, the cross section is even more than this side, right? Now, this cone sphere is a good example to illustrate the fundamental characteristics of radar scattering than the sphere because it has three different aspects to be viewed. In cone sphere, the echoes from the tip, that is this part, and the join between the cone and the sphere, as well as the creeping wave that travels around the sphere. Okay, we have three things. Okay, these are the three echoes. So one echo is from the tip, then is from the ear, and then the creeping wave echo. So there is no backscatter from the sides of the cones. Okay, when viewed from the nose on aspect, and assuming that the surfaces are smooth. So that is one assumption. So in practical concept, this tip will not have a zero radius. Okay, so it is assumed to have zero radius, but practically it will not have zero radius. But it will be rounded, and that rounded tip can also contribute to total cross section of the cone sphere. So the result of this rounded tip and the surface roughness. I mean, we assume that the surface is not smooth, but then there will be some roughness. And we assume that the tip is without any radius, but then there is the radius. So result of this rounded tip and the surface roughness and the imprecision of target surface contour here is that the cone sphere cross section will no longer decrease with increasing frequency. Increasing frequency means lesser lambda, right? If this is becoming lesser, this becomes larger. That is 2 pi by lambda becomes larger, right? So because of these things, this cross section will no longer decrease with increasing frequency. So we have a graph like this. Okay. but will level off and even decrease at higher frequencies. Okay. Higher frequencies means lower lambda. Lower lambda means this expression is higher. That's why it is decreasing at higher frequencies where other factors dominate. That's why we have such a graph. Okay. So this was about cone sphere. This is one figure which is a measured radar cross section of a cone sphere with a cone sphere angle of 225 degrees. So you can see the echoes are more here, and then this is the backside sphere. Okay, so this is measured. Okay, the scattered object is measured. This is one example of cone sphere which is measured. Fine. So that was about sphere and cone sphere. Any doubts? Please revert. You can ask in WhatsApp or call me, or when we have the live session tomorrow, you can ask. Okay. Thank you. I'll just show you. I've written all these things in notes again. Okay. So in the previous year, this question was not asked, but then yes, this is important. And when this is asked, you should write about the two simple targets and the graphs related to them. Okay. So this was the question which I showed, which was related to the previous topics. And in the notes also I've written radar cross section of targets with the detailed explanation of all these areas, and then the explanation of sphere with the graph and the three regions, and about the specular return and trippy wave, and then about the cone sphere and the figure. Okay, written in detail, just go through it. But then you have to listen to video first, and then I'll upload the notes. Okay, so thank you. So I'll upload the next video later. Tomorrow we'll have a live session on next topics. Okay.